Okay, this is the screencast for 4.6 example 2. Example 2, we want to verify, that is pronounced periodicity, verify periodicity algebraically. So to verify algebraically that f of x equals sine of x squared is periodic and determine its period graphically, we're going to approach this process very similar to plugging in negative x when we tested symmetry last semester. We plugged in negative x last semester to test what would happen to the x values that were negative. Are they going to be the same as the x values that were positive, the opposite of the x values that were positive, or neither? So now we know that the sine of x function is periodic with period 2 pi. Therefore, the sine of any x value we pick is the same, is exactly equal to the sine of that same x value plus 2 pi. So in other words, 2 pi later down the x-axis, you're going to have the same exact y value. That's why a sine function repeats itself every 2 pi. So we're going to use that for help with our proof. First, we're going to start off with our original function. F of x equals the sine of x squared. Well, I know that f of x equals the sine of x squared. I want to know what's going to happen to the f of x plus 2 pi. So I am going to plug in x plus 2 pi and see what happens. Now, the inside of this composition function is sine of x plus 2 pi. And as we discussed, the sine of x plus 2 pi has the exact same value as the sine of x because the sine function is periodic. So we can reduce this or simplify that down or substitute it for just plain old sine of x. Now, the original function states that f of x equals sine of x squared. Now we have proven that f of any x value we pick plus 2 pi is that same exact y value. So, since f of x is the same as f of x plus 2 pi, and they are both sine of x squared, the function is periodic. Now, just because a function has the same value every 2 pi doesn't mean its period is 2 pi. As you can see in the example over here that I graphed y equals the sine of x squared, specifically in the typical window I use on the calculator, negative 2 pi to positive 2 pi for my x min and x max, and my x scale is pi over 4, and my y min I use is negative 5, and then my y max is positive 5. As you can see, the period of this function is pi. That does still mean that every 2 pi has the same value. For example, f of 0 is 0, f of 2 pi is 0. It just repeated itself before that as well. So we only proved that it does eventually repeat. We didn't prove how early it repeats. We had to use the graphing calculator to figure out that the period was pi. The now try problem is example number 9, or is problem number 9. Trying to get the window right here. So problem number 9 says verify algebraically that the function is periodic and determine its period graphically. So we're going to approach this proof the same as we did the last one. We know cosine is periodic. So if f of x equals cosine squared of x, which, by the way, this also means this. I know mathematicians like confusing you, but a square after the whole function means the same as a square here. right after the cosine. This is how you would have to enter it into your calculator, though. As a matter of fact, I will show you exactly how to enter it into your calculator in a second. Okay, so we start out with f of x equals cosine squared of x. We want to make sure that when we plug in x plus 2 pi, we'll get the same value we started with. Oh, forgot to plug in 2 pi. Now, since we know cosine is periodic, the cosine of x plus 2 pi is has the same value as the cosine of x. So we just showed that f of x is cosine squared of x, and so is f of x plus 2 pi. We show that they both have the same exact value. No matter what value, no matter what x value we start with, that x value 2 pi later will have the same exact y value. So, since f of x equals f of x plus 2 pi, and they are both equal to the cosine squared of x, the function is periodic. Now I wanted to show you a little bit more in detail how you would go about sketching this graph. Let's say if you didn't have a calculator, and yes, don't worry, you do have a calculator sitting in front of you, no problem. As we can see from the graph, the period of cosine of x squared is pi. Oh, and this is how I would enter this into my calculator. Your calculator is programmed to understand that a square after a closed parenthesis around the x means that you're squaring the whole function. It knows that. If you wanted to square just the x, you would need a square on the inside of the parentheses. So this will produce the correct graph on your calculator. Now, f of 0, we know is 1. We can see that right here. But to show you what that means I'm plugging in 0 for my cosine function. So the cosine of 0 squared, well, let's see, cosine of 0 for my unit circle is 1. So we're really taking 1 squared, so that is 1. I could do f of pi over 4. Cosine of pi over 4 squared. Well, the cosine of pi over 4 is square root 2 over 2. If I square that, I get 2 over 4, which is 1/2. So pi over 4 comma 1/2. It's a comma. Pi over 4 comma 1/2 is a point on my curve. How about f of pi over 2? The cosine of pi over 2 squared means I have to first evaluate the cosine of pi over 2, which is 0. And 0 squared is 0. So pi over 2 comma 0, pi over 2 comma 0, right there, a point on the curve. The cosine of 3 pi over 4 squared, well, the cosine of 3 pi over 4 is in quadrant 2, so that will be negative square root 2 over 2, but I still have to square it, which is going to make it positive again. So that's going to be 2/4 or 1/2. So 3 pi over 4, comma 1/2 is a point on my graph. Last but not least, the cosine of pi. The cosine of pi squared. The cosine of pi is -1. We're still squaring it though, so the final value is 1. Pi comma 1 is the last point in that period that I have evaluated. Notice I use the same points, the same starting x values as when I graph a tangent curve. Those just worked out well for me. If I know that I'm squaring my values, so if I square root 2 over 2, that square root disappears, and that's an easy value to work with.